this video, we are going to discuss about graphs in Java. So let's get right into it. If you've done your studies sequentially, then you've probably already familiar with the various data structures that we've learned, such as arrays, linked lists, or binary trees. These data structures all represent data and how we store them, maybe even the relationship between them. But of all data structures that we've learned so far, they all have some serious flaw. It's that the relationship that they have are rigid. For instance, in binary trees, there is only parent and child relationship, or a parent and its two-child relationship. The connection between a child from, say, a right subtree to a left subtree is non-existent. In linked list, each data can only be connected to the next data, or previous. In arrays, there is almost no relationship, except it is sorted. Now this is where a graph comes in. In graphs, each data can be connected to each other, like our picture of shapes here. Graphs can represent a lot of things. For example, the internet. Each object is connected to each other in a line of connection. Your laptop, for instance, is connected to the local wireless router, and so on. Another example would be connection between cities. For instance, the distance between city A and B are 40 kilometers. Distance from A to C is 30 kilometers. So the distance between C and B is 50 kilometers, for example. The most important thing about graphs is that each data has the potential to be connected to every other data in the graph. Moving on, there are two main components in graphs. One of them is basic objects, which are called vertex. It points to each of these circles or datas. The other one is the relationship itself between objects, vertex, which is called as edges. So remember these two terms. The data or objects is vertex. The relationship is edges. Okay? Before we continue, there are actually two kinds of graphs, one of which we have already seen. It is undirected graph, and the other one is directed graph. It's pretty obvious. The only difference is that the directed graph has a direction in it, whereas undirected graph does not. Also, there's another variation of graphs which is called weighted graphs. In these graphs, the relationships between the datas or the edges have weight. In other words, they have a value. This is for when you want to store the data for the distance. For instance, this in the cities example I mentioned earlier. Now that we know all about graphs, how do we implement it in Java? Well, there are lots of ways to implement graphs if you understand it well enough. There's data and relationship. You just have to figure out how to store the datas and how to connect them. Maybe store the relationship, I don't know. But in this video, I'm going to show you how to implement graphs by using an adjacency matrix. An adjacency matrix is basically a table which will store the value of the edges between them, like this picture right here. As some of you may have probably imagined, we are going to use a 2D array to implement this table. In the matrix, the index itself is the vertex. So, like here, 1 until 5 are all vertexes, and edges exist if the value in the table is not null. Like in this example, you can see. For instance, if I want to check whether there's an edge between vertex 0 and 1, I check table row 0 and column 1. And if it isn't null, then there is an edge. Mind you that I'm creating an an undirected graph without a weight. So the relationship only has to be one, or maybe two, but let's just use one. But we could change the code easily if you want to put a value into the table, say for a weighted graph. So let's get right into the code. As always, I will be sharing you the code so you can analyze and run it yourself. So I will only explain to you the important parts of the codes. Now the first code we have right here is the matrix class itself. This class will store the table itself, the number of vertex or vertices and the number of edges. We start off by the constructor. In our main class, we will input out our how many vertex would we like, and this will be the size of the matrix. So we create here new integer 2D array with the size of v. Then we set the vertices to v and edges starting from 0, since there are no relationship between them. We then proceed to insert each of the arrays in the table to 0 using our double loop. This is not really necessary in some programming languages because the default value of integer is 0, but better safe than sorry, right? Now that we've created the table, we need to know how to add a relationship between the vertexes. This is actually the easiest part since we're creating an undirected, unweighted graph. We only need to add where the relationship is. Say we want an edge between 0 and 5. We simply insert table row 0, column 5 with 1, and voila, an edge has been created between 0 and 5. Don't forget to add the number of edges. Next, this is not really a necessary code, but for precautions, say we would like to add a vertex. Now, this is where the weakness of adjacency matrix really shows. Because we are using a table of arrays, we can't just add another row to the array. We need to recreate the array and copy the values from the previous array, as we can see right here. Also, why is it v times 2? Well, the reason is, since we're adding vertex, there's probably a good chance that we will add them again in the future. So why not just double the size of the array so we don't have to create a brand new array each time we add a vertex? If you've noticed, the problem with this is that there are lots of wasted memory. This algorithm is simply not efficient. There are other ways to implement graph using lists, but I think adjacency matrix is easier to get your basics right. Finally, this is the code where we would like to know about the relationship between the datas. It's pretty straightforward. We simply check if the table at the particular row and column has a value of 1. So we are at the end of this video. Thank you for watching, and don't forget to like. Peace.